lecture series that we are going to start of the subject strength of material. So this subject holds a very high weightage in the GATE exam as well as in the ESE and the SSC JE exams. So this subject is very important, and it's a very scoring subject, so we can gain marks in that. And if we study it properly, if we have the concepts which are built in a good way, so we can get in gate also, like we can get 6 to 7 marks only from this subject. So today I am going to start with the very first chapter, which is the properties of material and axial stress. So in this chapter, the very first thing that we are going to do is, the question which comes in our mind is, why are we studying strength of material, and also if we are studying the material strength, so from where this idea came that we need to have this strength and we need to test the strength of a material. So the question was actually that what actually resists the force inside a material. So why are we first of all testing a material? Because we need to create certain components, certain structures with the help of those materials. And on those materials, for example, it's a rod. So on this material, we will be applying some kind of force. And if the material is able to resist that force or not, like with the force, will it deform itself? I mean, will it become something like this? It will stretch and deform. So will it deform itself, or will it resist its deformation with respect to the force? That depends how the material is, how strong the material is. So what is the thing that actually resists the force that is created when the material is subjected to any external force? For example, you have let's say you have a rod, something like this, and you have a force like this, and then you cut a cross section here. This is x cross section. So when you see the cross section here, what you will see, this is the cross section now. So the force that you created, there will be, due to equilibrium, equal force in opposite direction will be generated, so that inside the body, it will be the force that is inside the material. So this force will oppose the action that's going on to it. So due to that, it will oppose the change that's happening due to this force, right? So that's the internal property of a material that will resist the force that's applying on it, right? So that's what a material is doing when any external force is applied on this. Now, if we go, what like how the internal forces are developed, what are the different internal forces, let's see. So we have for axial loading we are seeing, so the same thing that I explained in previous slide. So the member under axial load was something like this. It was creating axial force with length L, and then we cut the member at section AA, we cut it, and then the force is here. Now if I create the free body diagram of this right portion, I'll be having an internal force that will be due to the equilibrium, it will be generated. So keep the right portion in the equilibrium, internal force will act at the cut section, and it will be equal in magnitude and opposite in direction. So the free body diagram of the left portion should also be something like that, because from where this came, where will it go now, right? So equal and opposite force N should be generated, so that these two cancel out each other, and total effect is only for the external force. The internal forces will be totally cancelling out each other. So the nature of internal force, if the member is in tension, the internal force is tensile. So the internal forces are also pulling it, right? Pulling the object, so it's tensile. If the member is in compression, the internal forces are compressive. For example, if in this portion the force was something like this, so this will also be generated in compression only, right? So this is how the things work here. So, and the major thing is internal forces are not visible from outside. Only if we cut a cross section we can see this. And why it is not visible? To maintain the equilibrium, because at the end externally if we are seeing, so these both ends are cancelling each other out. So these are the internal force developments that will happen. Now the thing that comes in our mind is a question that why force is not enough. So let's understand it with some example of something like this. There is a rod and then there is another rod. Okay, I am applying same force P, tensile force P. So will it create the same effect on both the bodies? Like this body is the bigger one, large body, and this is the smaller one. So it's a small body. So will the same amount of force generate the same effect on different type of bodies? So it is definitely a no. Because for example, like if we have a big table and on which we have a very big structure of metal, for example iron. So if I am just pushing that, I will not be able to push with the force. And then if on the table there is something of the same size or of smaller size of iron material, if it is like for example it's a Rubik cube. So if I apply the same force the on the Rubik cube, the effect will be different. It will just slide with the force, right? So force is not enough alone. We need to have one more criteria that will define what's going on, right? So force is not enough alone. We need to have another criteria, which is area. So if I apply 1000 Newton force on two bodies, both will not show the same effect, right? So we need to have a quantity that includes area. So for example, so from here we understood that force alone is not enough, right? And we need to have a quantity which is including area as well, which has force, and then that has area as well, which should have both. So for that purpose we designed a new term. So what was that new term? So we designed the term which is called stress. It represents the intensity of internal force. What's the intensity? And it's denoted by sigma, and it's given by force upon area, force per unit area. So if a unit area is something like this one, how much force is there on this unit area? So it's defining the intensity, right? So force per unit area is nothing but intensity of internal force. So it is nothing but stress. So, stress is not a quantity that is already available. We generated it. We created a new quantity that can define proper the effect of force that's happening on different bodies. So for that we generated a new term which is known as stress, and stress is force per unit area, and that means Newton per meter square, right? So this is what stress is and how the stress came into the picture. Now we have stress at a point. So these are different stress diagrams. Okay, and first, like before understanding this, let's understand the next topic, which is types of stress. So stresses are of two types. We have normal stress, and then we have shear stress. So on any body, like tensile stress. So if this is a body, and if the force is acting like this, so it's P, or if the force is acting like this, so from, and this is the cross section, right? This is the cross section of the object. So the, if cross sectional area and line of action of force are perpendicular to each other, we'll be calling the stress as normal stress. Okay, and there can be some forces like the sliding force or shear force. So, if cross-sectional area and line of action of the force are parallel to each other, we'll be calling them as shear stress. So, shear stress is parallel to the cross-sectional area, but and normal stress are generated normal to the cross-sectional area. Okay, and shear stress is denoted by tau, and normal stress is denoted by sigma. Okay, so we have stresses of two types, normal and shear. And now we understood internal and external forces. The forces which are applied from the on the body from the outside is external force, and the forces which are generated due to the reaction to maintain the equilibrium are known as internal forces, right? So we can have, so for example, let's say we have a body. So we have a body something like this. It's not. Uh, so we have a body something like this, and on this we have several forces acting on it. Like this is P1, and this is center. Okay, P1 is acting somewhat different, eccentric from the center. We have P2, which is specifically acting on the line of the central line of the body, and then we have P3, which is acting like this. Okay, now we let's say we cut a section like this. We'll be cutting the beam here. From after cutting this, what we will be seeing on the section, so this is the cut section. Okay, so from this cut section, what I'll be seeing is, see, there is eccentricity. Due to the eccentricity, a movement will also get generated, right? So we, what I'll be seeing is a force into the x direction. What I can see, a force generated into the y direction, and there will be a movement generated into the x direction, and along with that, what else can I see? In the same way, I can see the force movement generated in uh, I can say my, right, in my, and then I can uh, yeah, and I can also get a force something like this, which is fz, right? And in z direction also I can see movement generated, which is mz, right? So the forces can be any of them, but the internal forces which will be generated will be 6: fx, fy, fz, mx moment, my, and mz. So these are the maximum number of internal forces that can get generated into a 3D body, right? So there will be 3 moments and 3 forces. So, and the direction of movement can be calculated with the help of a right hand thumb rule, right? So this is how the forces will be generated. These are internal forces, and what I can say from the cross section, can I say that fx is, uh, should I write it here? So can I say that fx is nothing but it's a normal stress? So uh, it will generate normal stress, but the force type is, it's an axial force, it's in the axis of uh, the body, so it's axial force, right? Fy and Fz, so these are parallel to the cross section, right? Fz is parallel, Fy is parallel, so can we call them as shear force, right? And can I call mx, can I call mx as the torsional moment, because it will just rotate the uh, rod, right? So we can call it as torsional moment, right? And my and mz, we can call them as bending moment. See, my will bend the beam in this direction, mz will bend the beam in this direction, right? And mx will just like will create torque in the beam, so we will call them torsion. So these are bending moments. So this is how we have the types of stresses, and this is for 2D case, right? And sorry, 3D case, and in 2D also we'll be seeing the things same similarly. Now, yeah, can I see now here in this body we have, see, sigma x is the stress generated in the normal direction to this cross section, right? And this sigma y and sigma z, and there will be tau xy and tau yz, tau yz, tau xz, sigma y in this direction. So see, so at a point inside a body, at an infinitesimal cube is considered. So this is a very small cube which is considered inside a material. Now stress will be acting on all sides of that material, right? So stress is, and obviously stress will not be same everywhere, and it will vary from each point to other point. So we'll be defining stress at a point. So this is a very smaller point, and it is a cube in this case. Okay. Now we have normal stresses and then we have shear stresses, right? So normal stresses, we have sigma x, sigma y, and sigma z on all the faces, like face normal to x-axis, face normal to y-axis, face normal to z-axis, right? So these are normal stresses, and shear stresses will be parallel to the faces, so parallel to this face, x face, right? So tau xy is on the face normal to x, acting in y direction, so the second one will give direction. So tau first will give uh, uh, plane, and the second will give you the direction. So on the plane x in the direction y, tau xy. On the plane x in the direction z, tau xz. On the plane z into the direction y, tau zy. So this is how the shear stress works. And we have some key points that are, stresses vary from point to point. This we have to remember. Positive directions are assumed as shown. So you see whatever is mentioned here, outward is positive, in this direction only positive, y direction if it is there, so it's positive. So these are the positive directions, and these stresses maintain equilibrium of the infinitesimal cube. So this small cube is in equilibrium if it is having these stresses. So now let's move on to So stresses we studied. Now we have stress tensor. So it is nothing but it's a representation in the form of matrix of all stresses at a point. Okay. So we have normal stress and then we have shear stress. All these I have to show. Okay. So the stress tensor sigma ij, it is the 9 components of stresses at a point are arranged into 3 by 3 matrices. See, tau xy uh, will be there, and then we have tau yx also, right? So we have 6 types of shear and 3 types of normal stresses. We have 1, 2, 3, 4, 5, 6, 7, 8, 9. We have total 9 types of stresses which are generating on a body from all the sides, and all the 9 types of stresses will be arranged in form of a matrix. That matrix is known as stress tensor. So in this matrix, in diagonal, we'll be putting the normal stresses, sigma x, sigma y, sigma z. Now, like remaining the other shear stresses will be putting on the different locations. For example, so this is x-axis line. So in x plane in y direction, x plane in z direction, y plane in x direction, y plane normal direction, y plane in z direction. Z plane x direction, Z plane y direction, Z plane z direction. So we you can see somewhere it will be in some books it will be written sigma xx, sigma yy, sigma zz. Right. So it's nothing but in x direction, in y direction, in z direction. Okay. So yeah, and yeah, we have another point that so in general, tau ij will not be equal to tau ji. That means tau xy will not be equal to tau yx. So this is a general case. But for static equilibrium, we have to make sure that tau xy is equal to tau yx. So this is true for static equilibrium and for symmetric tensor. So this is also we need to remember. Now, so these are some more things about stress tensor. So at a point, infinite planes are possible. So each plane has different stresses. So we need a systemic representation, and then stress tensor is a bookkeeping system for all possible stresses at a point. So at a point there are like 9 types of possible stresses which can be there. So what you will be doing, you will be just putting that in form of matrix so that you have a record for that particular uh, point of all the stresses. So this is what stress tensor is. Now, the next question comes. So, we understood that we needed to test the materials because we had to make some structures, and in order to test the materials, we are applying force to that. And we saw that the material was resisting that force, the resisting the change that is going to come due to that force. If that is tensile force, the material will stretch and it's resisting that stretch. If it is compressing a compression force, the material will try to compress. So and the material was not compressing, that means it was resisting that compression, right? Even in shear, if the force is of shear, the material was not deforming in terms of shear. So there was some kind of resistance in that. So with that we came to know that there were some internal forces that were generating into the body. But then we saw that forces are not alone enough to judge a body of the due to the like for the deformation. So we needed to have another quantity, that is area, to be in account. So now force and area are two important things. With that we'll be judging a material. Now that quantity which came due to these two quantities, which is force and area, is known as stress. Now we saw what are stress, what's the unit, and we saw the types of stresses, we saw the stress tensor, how we keep the record of the stress. Now now we know that body is in under stress, body is generating stress. Now what will happen? So if it is if the stress exists onto the body for longer time, the body will deform. That's why you see the RCC structures, the roof of the structure, after some time you'll be seeing there will be little bending into that. Okay, so and little cracks can be generated. So there is there is prolonged stress on the body, and due to that the body deformed, right? So if stress exists, material must respond. So how the material responds? By deforming. So for longer time, if this is a body, right? So for longer time, if there is some kind of this kind of force is there on the body, though, then the body will have to respond to that, right? After some time, it will be in this type of shapes. That means it deformed from its original position. It has become something like this. Now, this deformation, how do we calculate this deformation? So for this, there comes another term which is strain. So for this, we came to strains. So what is strain? Strain is nothing but it's a measure of deformation. So how much deformation is there? We'll be measuring with it with the help of strain, and it's not a force, it's not even stress, but it will be and see one more thing, stress cannot be measured, but strain is visible. Stress, because I told you that stress was the quantity that we created, and there is nothing in the world that can directly there is no type of equipments or machines still developed which are not which are able to measure the stress. There is nothing like that. So in today's world, how will we measure the stress? We will check the deformation, because deformation is visible. So if we can measure the deformation, we can calculate the strain. Strain is nothing but measure of deformation, so we can calculate the strain. And if somehow we relate that strain to stress, we can calculate stress indirectly. That means strain is measurable and stress will depend on that. How much deformation is that? We can calculate depending on that how much stress was on the body. So strain tells us how much the material has felt the stress, right? So and a strain will be denoted by epsilon. Now we have three types of strains. We have longitudinal strain, we'll be calling that normal strain as well, lateral strain or transfer, shear or angular. So see, the body is having this kind of force. After some time, from its original length, the length will increase. So let's say it's delta L, so it will become L plus delta L. So the longitudinal tensile strain will be epsilon L. Strain is nothing but here only I should write. So epsilon is nothing but change in length upon original length. So this is the formula for strain, and change in length will also be in meter. So if 1 meter of rod changes, there came of change of 0.1 meter. So the change will also be in meter, and original length is also be in meter. So it is a unitless quantity, right? So strain is a unitless quantity, dimensionless quantity, and its change in length per original length. So longitudinal strain you can calculate, it's nothing but delta L upon L, and this is positive. Strain is positive in tension. Now in compression, the length became was shrinking. So it's reducing. That means I'll be putting a negative. So compression is a negative strain. If there is increase into the length, it is positive. There is decrease into the length, it is negative. Now in lateral strain, what we are doing, see, this rod is having forces in this direction, so the rod will be increasing. So if this dimension is increasing, the length is increasing, so the width will be decreasing, right? Somewhere the material has to compensate. If it is increasing in terms of length, the width will obviously will be decreased, just like an elastic. So if I have a rubber band, if I will stretch that, length will increase and the width will decrease. So due to the increase in length, what is the decrease in width, right? So that will be your lateral strain. So this was, for example, this is original width, and after stretching, that this has become the final width. And so the decrease will be in, so here this much will be the decrease, right? So it will be b minus delta b. So decreased width will be b minus delta b, and the decrease is of delta b here, db or delta b. So this is delta b upon b, and because of longitudinal, because of tensile force, uh, the strain, because of tensile force, length is increasing, and the lateral dimension will always be decreasing. And due to the decrease in the lateral dimension, this lateral strain will be negative in tension. Okay. And then we come to shear strain. So this is a body which is something like that. If I applied a shear force like this and it is fixed here, what I will see, that upper part will be uh, moving, and there will be some angular change into this part. See, and we'll be calling that as gamma, and then it is known as shear strain or angular strain, and we'll be denoting it as gamma. The longitudinal strains and lateral strains are denoted as epsilon, longitudinal, epsilon lateral, but shear strains will be denoted as gamma. And gamma is nothing but the tan of theta. So gamma will be given as tan theta, and this change will be very small, that tan theta will be equal to theta, and its unit is in radians. So theta is change in angle. So this is what the types of strain are. Now we'll be seeing stress versus strain. We understood today what's stress, we understood what's strain. Now I told you that we can measure strain, and we had to uh, connect this strain to stress, so that we can calculate stress also. And now that part we'll be seeing into the further lectures. So I hope you understood the very first lecture, and I hope you continue this journey with me to complete this lecture series for strength of materials, and be prepared for next year's competitive exams. Thank you everyone.